Hello guys, welcome back to TechDose, and in this video we will look at fruits into baskets 3 problem, which is from Leetcode number 3479. The optimal solution in this case will be based on segment tree range max query solution. So you are required to know everything about segment tree, how to build a segment tree, how segment tree works, and also you should have already implemented the range max query problem. So I have made detailed videos on range sum query as well as the range max query. So you must watch my video on segment tree construction, range sum query and range max query. If you have not done segment tree, then you will not be able to solve this problem. Okay, so even though the problem is marked medium, I would have marked it as hard. Okay, so if you cannot solve this problem, then you should not get demotivated, because anyway it is a difficult problem, and if you know segment tree, then the solution will be easy to understand. Now let's read the problem statement. In this problem you are given two arrays of integers, fruits and baskets, each of length n, where fruits at I represents the quantity of the ith type of fruit, and baskets at j represents the capacity of the jth basket. From left to right, place the fruits according to these rules. Each fruit type must be placed in the leftmost available basket with a capacity greater than or equal to the quantity of that fruit type. Each basket can hold only one type of fruit. If a fruit type cannot be placed in any basket, it remains unplaced. We need to return the number of fruits that remain unplaced after all the possible allocations are made. Now if you look at the first example, given fruits 4 to 5 and baskets 3, 5, 4, we can go for each of the fruit one by one from left to right, and as soon as we see a fruit, that means type 0 fruit has 4 quantity, then we need to iterate on the basket from left to right and find the first basket which has a capacity greater than equals to 4, and that is this 5, right? So you can say that this 4 can be assigned to basket at index 1 and you are done. Now we cannot use the basket at index 1 even if it has capacity left over. Okay, we cannot use it because each basket can only hold one type of fruit. Now you go to the second fruit type, it has 2 capacity. Again iterate from left to right and find the first basket which has a capacity greater than equals to 2. Yes, it can also be assigned, and therefore you mark it so that you don't use it again. For the third type of fruit, the number of fruits are 5. Go again from left to right and find out the first basket type which has a capacity greater than equals to 5. So first and second are already consumed. The third one, which is not used, is having a capacity less than 5, so it cannot be used, right? So this third type of fruit cannot be assigned. So first and second type could be assigned, third type could not be assigned. So the total number of unplaced fruit types is only 1, and therefore the answer is 1, right? So if you follow this approach, you know that it is an n square approach, because for each of the fruit type you might have to iterate through all the items and you will find the last one suitable. For the second one you will find the second last suitable, and so on, right? Or maybe you have to iterate for all the items. So it will be an n square approach. And let's look at the constraint in this case. If you see, the fruits length and basket lengths are same and they are 10 to the power of 5. So if you write an n square algorithm, total computation will be 10 to the power of 10, which is beyond your 10 to the power 8 limit. So definitely it is going to give you a time limit exceeded, right? So we should not use n square. We should use an algorithm n log n or order of n. So we should not exceed n log n. We should be somewhat less than equals to n log n, you can say, right? Somewhat similar. In this case, all the values are within the range of 1 to 10 to the power of 9. That means everything fits within the 32-bit integer. So we can take integer, right? So I hope the problem and the constraints are clear. Now let's look at an idea which will help us solve our problem. Now since we know that we cannot use the brute force approach, let's try to use another logic. Let's say that I am trying to place this first type fruit. Now if I say that I will be dividing these baskets into 2 regions. Let's say this is region A and this is region B, and I am dividing it, let's say, in the middle. If I say that the maximum item in the left hand side region is 9 and the maximum item on the right hand side region is 7, then I just want a basket which is having a capacity greater than equals to 3. and I want it at the leftmost index. These are the two conditions that I want to check. The capacity of the basket must be greater than equals to the type of fruit that we are looking at. That means the type of fruit 0 has quantity 3. So my capacity of basket must be greater than equals to 3, and it should lie to the leftmost index. That means I have to iterate from left to right and find it. Okay. Find the first basket where 3 fits. So if I know that if I had divided this entire basket into two parts, the maximum on the left is 9, the maximum on the right is 7. These both can actually contain this fruit type 0, which is having 3 quantity, right? But since I want the leftmost index, I will be searching on the left side and I will be ignoring the right side. Okay, I think this makes a lot of sense. Now once you know that, you will be exploring on the left side. You have 9, 4 at index 0, 1. Let's divide it into two parts again. And on the left side you get the maximum capacity as 9, and on the right side you get the maximum capacity as 4. Then this means that they both can contain the type 0 fruit, but since I have found it on the left hand side, I will always choose the left hand side greedily and not choose the right hand side. So choose the left hand side, and now you are left with only one basket. So this will be assigned to fruit type 0, that means which is having a capacity 3. So if you do this assignment, then I have to mark it as, let's say, -1, so that you don't end up using it again. Okay, so I will not be saving any positive number. Let's say I saved a negative number. Okay, so because the capacity cannot be negative, so I marked it -1. So this could be assigned. Now I will be checking for this 8. Now if you again go and check for 8, then again I will be following the same process. Now my array is -1, 4, 7, 5. And now if I divide this into two parts, and let's say on the left hand side I say max is 4, and on the right hand side the max is 7. Since this capacity is 8, I know that none of these actually satisfy the capacity 8. Therefore it is useless to search. So this cannot be assigned. I can say this cannot be assigned. Okay. So I can maintain a counter which will start from 0, and it will always be incremented when some fruit type cannot be assigned, right? Now I can go to the third fruit type, which is having 6 quantity, and I will use the same array -1, 4, 7, 5, and find out. On the left side the maximum is 4, on the right side the maximum is 7. So which side should we choose? I will always greedily choose the left side, but on the left side the maximum is less than 6. So if I go to the left side, none of this basket will be able to contain the fruit. Okay, so I will be going to the right side. This makes sense. Now you have 7, 5. On the left side the maximum is 7, on the right side the maximum is 5. Now if on the left side you have the maximum value greater than equals to 6, I will always choose the left hand side because I want the leftmost index. So let's go on the left hand side. You are only left with 7, so 7 will be the one which will be assigned to this 6. Okay, so we will be marking it as -1 now, so that it cannot be reused. Now you go to the third type. I mean you can say the last fruit type. Okay, now the array is -1, 4, -1, 5. Now in this case again you divide it into two parts. On the left side your max value is 4, on the right side the max value is 5, and you are finding for capacity greater than equals to 1. On the left side, is the capacity greater than equals to 1? Yes, the max is larger, so you will search on the left side -1, 4, and then see on the left side the max is -1, on the right side the max is 4. So on the left side, is the capacity greater than equals to 1? No. On the right side, is the capacity greater than equals to 1? Yes. So go on the right hand side. Okay, and now you will only be left with 4, so this 4 will be assigned to this one, and so you will be marking it as -1, and this is also assigned. So after doing all the assignments, you know that index 1 is the one that was not assigned, and the count value will tell how many fruit types could not be assigned. Okay, so if you follow this approach, you can solve this problem, right? And since we are always dividing this array into two parts, so if you have an n size array, then I will be dividing it into two parts, into n by 2, n by 2, and again further dividing them into two parts. So you know the height of the tree diagram is going to be order of log n base 2. Okay, so for each query you can actually search for the assignment in log n time, and if there are n number of queries, you can solve this in n log n time. This concept was used in merge sort, binary partition top down. Okay, so how do you maintain this thing? If you have already solved segment tree range max query, then you know that this particular thing can be implemented with the range max query in the segment tree. Hence we will be going for the segment tree, because segment tree is same as your merge sort binary partition. When you do top down, then you do binary partition on the array. Okay, and when you move bottom up, then you take the maximum of the left and right, so you can say range max. When you go bottom up, you maintain the range max. So on this entire array of baskets, I will be dividing it by using binary partition. So you can say that 9475 will be the initial array, and its range is from 0 to 3, and that is why I have written here, you can see 0 to 3. If you divide it into two parts, on the left hand side you will have 94, on the right hand side you will have 75. So on the left hand side you have the range from 0 to 1, on the right hand side you have the range from 2 to 3. You can see this skeleton, it is looking the same, right? When I go on the left side, it is just 9, on the right side it is just 4. So this is index 0, index 1. So 0 to 0, 1 to 1. You see here 0 to 0, 1 to 1. On the right hand side you will have 7 and 5. And if you see the index 2 and 3, so this is 2 to 2 and this is 3 to 3, 2 to 3 and 3 to 3. So these nodes will be containing the maximum in the given range. So 0 to 0, what is maximum? It is just the array item. So all the array items will be filled here, 9, 4, 7, 5. And as you move up, the max of left and right will be taken. Max of left and right will be taken, max of left and right will be taken. This is how you build the segment tree range max query problem, for the range max query problem, right? Now once it is built, we will be applying the same logic. We will be assigning the fruits one by one. So we will be going for each of the fruit. Let's go for the first fruit. We will be keeping a counter, count equals to 0. Whenever I cannot do the assignment, the counter will increase. Now let's start from the beginning. Now we have to check that if 3 can be assigned or cannot be assigned in this segment tree. So if the maximum value in the range is actually greater than equals to 3, then the assignment is possible. So yes, the assignment is possible. Now look at the left child and the right child. You know that in the one based indexing segment tree, if this is index 1, this will be index 2, this will be 4, this will be 5, this will be 3, 6 and 7. You know, if the current index is I, then the left child will be a 2i index and the right child will be a 2i plus 1 index, right? So this is for one based indexing. If you do 0 based indexing, then for the current index I, the left child will be 2i plus 1, right child will be 2i plus 2. The formulations will slightly change. For any current index I, the parent index will be at I by 2. Okay, so this is how a binary tree is actually implemented using an array. Okay, now once you know this, let's see. Initially the segment tree index will always start at 1. That's what I'm assuming. So if this value 9 is greater than equals to 3, then the assignment is possible. So first of all, I will try to move on the left side because I want to find the leftmost index. So if the left child has a value greater than equals to 3, then I will be making a call to the left side. Yes, it is possible. 9 is greater than equals to 3. Again, I will try to make the left call because this 9 is again greater than equals to 3. Now when low equals to high, this means that you are looking at just a single item. It is a leaf node. And so when you have reached to the leaf node, then you have done this assignment successfully. Okay. Now in order for this not to be reused again, you set it to -1. And while returning, we will not be returning the exact value as -1, but I will be returning a positive value 1, saying that the assignment was done. This 1 will not be updating anywhere. It is just being returned. Okay. Just being returned as a positive value saying that the assignment was successfully done. Now when you reach here, then this value will be updated with the max on left and right. Left is -1, right is 4. So this will be updated to 4. And this will also return the same return value as 1. Now at this point again, this will be updated to the max of left and right. So this will become 7. And then this will also return 1. So this is how the assignment for 3 was done. Now let's try for 8. For 8, when you start at the root node, then you see that the root node has a value 7. This means that the maximum size basket which is present is only of size 7, and so 8 cannot be assigned, so you have to return -1 from here. So if it returns -1, then in the main function, in the driver function, you know that this assignment could not be made, and so the counter can be increased by 1. For the third index here, for this 6, I will be starting here, and you see that this value is 7, which is greater than equals to 6. So yes, the assignment can be made, but let's reach to that value. On the left side you have value 4, which is less than 6, so we should not move to left, we will move to right. On the right side again this value is 7, so check on the left and right. On the left you have a value greater than equals to 6, so I'll move to the left. Now here low and high values are same, this means I have reached to the leaf node, so this assignment is successfully done, I know that, and I will be resetting this value to -1 and returning the value as 1, saying that the assignment was successfully done. Here the value will be updated to max of left and right, so this will become 5, max of -1 comma 5, and then this will also return 1, saying that the assignment was successfully done. Here the max value will be max of 4 comma 5, so this will be updated to 5, and this will also return a value 1, that means this assignment was successfully done. Again for the last query, we will again be starting at this initial index. Here the max value is 5, which is greater than equals to 1, fine. On the left side, is the value greater than equals to 1? Yes, so I will go to the left side greedily. Now again here, from here on the left side the value is -1, which is less than 1, so I will not go to the left, I will go to the right. Here the value 4 is greater than equals to 1, so I'll go here, and here low is equals to high, so this is where I stop, and this value will be assigned. So since this is assigned, I will be setting it to -1 and returning a value 1, saying that the assignment was successfully done. Now at this point the max value will be updated to max of left and right, so this becomes -1, and this will also return a 1 value. At this point it will be updated to max of left and right -1 comma 5, it will remain as 5, and this will also return a value 1. Okay, so we are done with all the fruits query, and we saw that we could not do one assignment, and therefore the answer will be 1. Right, I hope this entire approach was clear. In this case the segment tree size will be 4n plus 1, because I am doing 1 based indexing. For 0 based indexing you can take 4n, or there is another way to find the height of the tree. Let's say the height of the tree is log n, then you know that I cannot have more than 2 to the power log n plus 1 number of nodes. It is just the formulation for the total number of nodes in a perfect binary tree of height h, which is 2 to the power of h plus 1 minus 1. Okay, so these all things have been explained in detail while doing the construction of the segment tree, so I will highly recommend you to watch that video as well. So in this case building the segment tree is order of n, because if you have 4n number of nodes in the worst case, then it will be order of n to build the segment tree, and you know that there are n number of fruits, and each of the fruit query will take height of the segment tree, which is log n. So I will be appending another time which is log n. So the total time complexity will be n plus n log n, which is n log n, and the space complexity is only due to the segment tree, which is order of n. So I hope this is clear. Let's now look at the code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. In this code I have defined the segment tree here, and this is the code for building the segment tree. It is exactly the same as I had explained in my other videos, so please watch that. Now I'm just doing top down binary partition on the range, and just dividing it into the middle, right? And whenever I'm done processing the left and the right subtree, then I will be updating it with a max of the left child comma right child. Okay, that's what I'm doing. If you look at the main function, number of unplaced fruits, we are getting the fruits and basket. I will be taking the fruits dot size as n, which is the same as the baskets dot size as well. Segment tree size will be 4n plus 1, because we are doing 1 based indexing and we cannot have more than 4n nodes. Now step 1 was to build the segment tree, which is for the range max query. We have already done that, and after this we will be querying the leftmost basket for each of the fruits. Okay, and if the fruit assignment cannot be done, we will get -1 as the return value, and so the counter will increase, and finally the count will be returning us what will be the uh, number of fruit types that could not be assigned the basket. Now if you look at the assignment code, here we are taking a fruit, the low and high range, and the segment tree index. Now if I know that the current max value in the entire range from I to j is, let's say, x, or let's say it is 10, and you know that the fruit value is 12, then there is nobody in the range from I to j in the basket that can actually accommodate this 12 number of fruits. So we will be returning -1. Otherwise, if we have reached to the leaf node, then we will be assigning a -1 value because we will be using that basket, so that it cannot be reused again. I will be setting it to -1, and I will be returning a value 1 showing that the basket was found and the assignment was successfully done, right? If we can do the assignment but we have not reached to the leaf node yet, then I will be finding the mid value. So we are doing binary partition in the range, and we will be making the left call and the right call. So the left call will be made if the maximum on the left hand side, is actually greater than equals to the number of fruits that I'm looking for. Okay, so if the basket size is larger than the number of fruits, then I will always prefer the left hand side, because the problem was asking for the leftmost index. Otherwise, if on the left hand side we don't have any basket which can accommodate the given number of fruits, then I have to go to the right hand side. I have no other choice. Okay, so the range will be divided. If you go on the left side, you will go from low to mid. If you go on the right side, it will be mid plus 1 to high, and accordingly the segment tree index will also change. From the st index I, it will be 2 times I on the left side and 2 times I plus 1 on the right side, as it is written here. Okay, and finally we will be coming back to the node whatever is the query done, and so the maximum value have to be again reassigned with the max of left child comma right child, as I had shown you in the dry run, and we will be returning the same value as we got as the return value. So if the assignment was successfully done, I will be returning a 1 value, otherwise I'll be returning the -1 value, right? So I hope this entire solution is clear. If you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. See you guys in the next video. Thank you.